All right, hey everybody. So now that we have the first fundamental form and the second fundamental form as tools that we can use, I want to go back and look at the Gauss map, specifically the differential of the Gauss map. And up until now, the differential of the Gauss map has been slightly hard to work with. We've really used three facts about it. We've used the fact that if you plug in the vector x sub u, you get n sub u. If you plug in the vector x sub v, you get n sub v. And finally, the fact that this differential is linear, right? So that linear combinations of xu and xv will get as outputs the same linear combinations involving nu and nv. And so that has been great, but for many of our maps, right, especially many of our functions, say from R2 to R2, we want to be able to write them as a matrix, right, a 2x2 matrix. We have a 2x2 matrix for our first fundamental form, a 2x2 matrix for our second fundamental form, and it turns out we can come up with a nice matrix for our differential as well. So let's take a look. First of all, as a reminder, our differential map, right? Well, the Gauss map itself was from a point P on our surface to the point n sub p on the unit sphere. And so the differential was a map between these two tangent planes. However, our tangent plane at n sub p of S2 was parallel to the tangent plane at P of the point S, and so we tend to think of this as just being a map from TPS into TPS, right? Where associated vectors are identified because they are lying in the same or parallel planes. We know these two facts, and we know the fact that this differential is linear, but we might ask ourselves whether or not we can come up with a matrix to represent this Gauss map, or this differential of a Gauss map. And so our goal then is going to be to come up with a expression. Let me actually go back a slide. Our goal is going to be to come up with an expression like a matrix, which I guess we could call it a matrix M. Notationally, we will use this notation of A1, 1, let me cheat and make sure I get this right, A1, 2, A2, 1, and A22, we'll be using this matrix notation to define the matrix of our differential. Notice we're doing something a little funny with our subscripts. One of the subscripts is going to become a superscript, but these are not, I just want to say, these are just indices. We are not actually taking a number and squaring it. This is the entry A21, just that first two is a superscript. And so the goal then is that if I were to plug in a vector, right, if I were to take a vector w and try to apply this differential to it, I could hopefully get a representation of w by writing it in vector and matrix notation, and then the differential of w should hopefully just be this matrix times the components of w. Now, a few things about that, right? First of all, so this matrix is what we're hunting for. These aij's are still unknown quantities to us, and our hope is to be able to figure out a way that we can compute these aij's. Secondly, oh, looks like I'm missing a little arrow there. Yeah, secondly, because we're working within our tangent plane, right, the standard way that we would write our basis vector is not using I and j or ijk. Instead, our standard basis vectors for our tangent plane have proven to be x sub u and x sub v, right? And so when I write w, and I want to write it in its component form, w1 and w2, what I really mean is w1 x sub u plus w2 x sub v, because those are my two main vectors in the tangent plane, my two basis vectors. Now, for this video, I'm going to be replacing my subscripts u's and v's with the numbers 1 and 2, just because we'll end up doing a lot of sort of subscript i's and subscript j's, and I just want them to be thought of as either representing 1s or 2s, aka either representing u's or v's. So w is written as w1 x sub 1 plus w2 x sub 2 is written in its component form like this. And then we know, because we know about, this is like one of the two things we know about our differential, is that if I plug that vector w into the differential, I get w1 n sub 1 plus w2 n sub 2, right? Because we send x1 to n1 and we send x2 to n2, and because this differential is linear. Now, so that is what we know the output is, but we're also interested in knowing if I am able to come up with such a matrix, what would that output look like? And so we compute this output, right? If I do my matrix multiplication correctly, I would get A11W1 plus A12W2, right? And that's going to be my top entry, plus, oh, I should say, and then for my second entry, I would get A21W1 plus A22W2. Right? And those would be my entries in my, I should say, as outputs in my basis, which means that my new vector, which I already know to be this vector up here, could be equivalently written as, I guess I'll do this down here, this could be written as A11W1 plus A12W2, right? And that top entry, right, corresponds to our x1. So this is like my x1 plus, and then the second entry is A21W1 plus A22W2 times x sub 2. Right? So in other words, I know, because it's one of the 2 or 3 things I know about this differential, I know that my output of my vector w is equal to this. At the same time, if I want to come up with a matrix representation, I know that my output should also be equal to this. And so hopefully I can find these coefficients aij that will make these 2 things equal to each other. That's sort of my hope here. And to do that, I'm really interested in, and I should say that such coefficients should work for every choice of W1 and W2. And so my hope is that such vectors can be found. The difficulty, of course, is that up here this is written in terms of n1 and n2. Down here this is written in terms of x1 and x2. And those might not be the same, they might not be pointing in the same direction. And so it's hard at the moment to translate between these two. So let's simplify things down a little bit and start coming up with clever equations that can help us. The first thing I want to do is to say that if this equation should hold for any function, coefficient w1 or w2, in particular, it should correspond to when w2 is equal to 0. Right? And so if w2 were equal to 0, how would that affect things? Well, I should say maybe up here, if w2 is equal to 0, that means that I'm plugging in this vector. My output down here would just become w1 n1, because 0 times n2 is just 0. And so as a result, what I would get down here is, this is a 0, w2 is a 0, so each of these terms get knocked out. And as a result, this term is gone, this term is gone, and I get the equation that says w1 n1 is equal to a11 w1 x1 plus a21 w1 x2. So we get this expression for our n1. Also notice if I set w1 equal to 1, then my w1s would cancel, or alternatively, I can just cancel my w1s right now. So w1, 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 and I get the equation that n1 is equal to a11 x1 plus a21 x2. And I can do a similar thing to figure out a way to represent n sub 2 as well. And the results are down here. So n1, right? Let me scroll up for a second. We said n1 was a11 x1 plus a21 x2. I can write that in its component form as a11, a21, right? That's exactly what I found. And by an equivalent argument, I can find that this is true as well. So this is my vector representation for n2. Great. So now we have a way to represent n1 and n2 in terms of x1 and x2. At the same time, we have our second fundamental form, which told us that we could calculate, we could calculate our second fundamental form as a dot product. Individual entries were dot products of n sub I dotted with x sub j. Right? So to go back a slide, here I have some equations that involve n sub 1 and n sub 2. Right? Going forward, I have something involving the dot product of n sub I, so n sub 1 or n sub 2. And my ultimate goal is to solve for these a's, right? To figure out what these a's are. So to try to uncouple the a's from these x's and to try to start isolating and figuring out the a's, I'm going to bring back in my second fundamental form. And in particular, I'm going to replace my ni, what I am hoping to isolate here, with what I found on the previous slide, right? So down here I could write my n1 or my n2. And so here I'm just rewriting that, the n1 or n2. Here I'm just calling it n sub I. And so n sub I is a1i x1 plus a2i x2. And that will then be dotted with xj in order to get my second fundamental form, my negative lij. Now, of course, dot product is linear, so this distributes. And then I get the expressions x1 dotted with xj and x2 dotted with xj. But that is exactly my first fundamental form, right? x1 dotted with xj was exactly the entry